In order to understand electronic structure of atoms, we first have to understand something about the properties of waves. Waves have length, symbolized by lambda, amplitude, the height of the wave, and frequency, symbolized by nu. The speed, u, of the wave is equal to lambda times nu. Maxwell proposed that visible light consists of electromagnetic waves. There is an electric field component and a magnetic field component. These are perpendicular to one another. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. All electromagnetic radiation follows the formula wavelength lambda times the frequency nu equals the speed of light. Here is a chart showing the wavelength and frequency corresponding to different types of radiation. Notice that visible light, what we can see, is a small part of the electromagnetic spectrum. It ranges from 400 nanometers to 700 nanometers. Here's an example. A photon has a frequency of 6 times 10 to the 8th hertz. A hertz is per second. Convert this frequency into wavelength, nanometers. Lambda times nu equals c, the speed of light. Lambda is c divided by nu. Substituting in 3 times 10 to the 8th meters per second, the speed of light, divided by the frequency 6 times 10 to the 4th hertz, results in 5 times 10 to the 3rd meters, and converting that to nanometers, it is 5 times 10 to the 12th nanometers. In 1900, Max Planck solved the heated solids problem. When solids are heated, they emit electromagnetic radiation over a wide range of wavelengths. We've seen this. Red hot, white hot metal when heated. Energy is emitted or absorbed in discrete units, he proposed. He called them quantum. The energy, he said, was equal to a constant times the frequency. The constant is now called Planck's constant, 6.63 times 10 to the minus 34 joule seconds. Einstein solved the photoelectric effect in 1905, for which he won the Nobel Prize. He realized that metals emit electrons when exposed to light, and he theorized that light had both wave nature and particle nature. He coined the term photon, which is a particle of light. Here's an example. When copper is bombarded with high-energy electrons, X-rays are emitted. Calculate the energy in joules associated with these photons if the wavelength of the X-ray is 0.154 nanometers. The energy is Planck's constant times the frequency. Substituting in c over lambda for frequency, we can then calculate 6.63 times 10 to the minus 34 joule seconds, which is Planck's constant, times the speed of light, 3 times 10 to the 8th meters per second, all divided by 0.154 times 10 to the minus 9th meters. Notice that you have to change the nanometers to meters. This results in 1.29 times 10 to the minus 15 joules. If gas is excited by a high energy discharge tube and the light is passed through a prism, it results in line spectra. For hydrogen, the line spectra is as follows. Here's a table showing line spectra for a whole series of different atoms. They're sort of like fingerprints for these atoms. To explain this phenomena, Niels Bohr came up with a model of the atom in 1913. He theorized that electrons can only have specific quantized energy values, that light is emitted as an electron moves from one energy level to a lower energy level. The energy for the level can be calculated by setting it equal to minus RH, which is the Rydberg constant for hydrogen, times 1 over n squared, where n is the principal quantum number. 1, 2, 3. They are integers, and they start at 1 and can go theoretically to infinity. These are different energy levels. What energy does a hydrogen electron have if it is in the n equal 3 level? Very simply, substitute in to the equation E sub n equals minus RH times 1 over n squared. The Rydberg constant is a negative 2.18 times 10 to the minus 18 joules, and n is 3. It's 1 over 3 squared. The answer is minus 2.42 times 10 to the minus 19th joules. Here is a series of transitions in the hydrogen atom from higher energy levels to lower energy levels. There are 4 different series that have names: Lyman, Balmer, Paschen, and Brackett. These correspond to line series that were discovered by the scientists. The energy of the photon is the difference in energy between the final energy level and the initial energy level. This results in the equation R sub h, which is the Rydberg constant, times 1 over n initial squared minus 1 over n final squared. Here's a table showing the various series in the atomic hydrogen emission spectra. Notice that they hit the range ultraviolet to infrared. Calculate the wavelength in nanometers of a photon emitted by a hydrogen atom when its electron drops from the n equal 5 energy state to the n equal 3 state. Again, the energy of the photon, delta E, equals RH times 1 over n initial squared minus 1 over n final squared. Substituting in 2.18 times 10 to the minus 18 joules times 1 over 25 minus 1 over 9. The energy of the photon, delta E, equals a negative 1.55 times 10 to the minus 19th joules. To calculate the wavelength, we remember that the energy of the photon equals h times c divided by lambda. Solving for lambda, hc divided by the energy of the photon. This is 6.63 times 10 to the minus 34 joule seconds, Planck's constant, times the speed of light, 3 times 10 to the 8th meters per second, divided by the energy, 1.55 times 10 to the minus 19 joules. Notice that we take the absolute value of the energy. Lambda equals 1280 nanometers.